All right, algebra. Welcome back. Today we are talking about our last uh, exponential or last exponent property. This one deals with radical and rational. So let's start off by saying we have this cube here, and we want to find the length of the side listed for the volume. So we know in order to find the volume of a cube, we take one side times another side times another side. So, and because it's a cube, all those sides are the same. So it's essentially S times S gives you your volume. Well, we know S times S times S, side times side. That is just the same as side to the third or side cubed. That's where we get the word cubed from, or the phrase cubed, or why we do square is the second power because it's a square. The area of a square is the side length times the side length. So if I'm given a volume of 27, I want to figure out what are these side lengths? What is S equal to? Well, I have to think what number what number would be multiplied by itself side times side times side to give me 27. So S to the third equals 27 means what number times itself 3 times gives me 27. Well, 3 times 3 times 3 is 27. So S would have to be 3 because 3 times 3 is 9 times 3 is 27. Easy enough. What about 343 though? 27 I can probably get away with because I have that one in my head. 343 is a little bit harder because you might not know what number times itself 3 times gives you 343. I know that I personally only know it because I've looked it up recently, but I'm probably going to guess that you probably don't know that off the top of your head. But if we check, we might have to test a few things. 7 times 7 times 7 equals 343. That works, so we know our side length would have to be 7. But we might have to check a little bit on that. So there is an easier way on how to solve these, and that's with square roots or radicals or roots in general, not necessarily square roots. But we can use roots to help us figure out working backwards like these. So when I have a square root, it's essentially asking the question, what number times itself twice, what number multiplied by itself gives you 25? Well, I know the square root of 25 is 5, and my proof is because 5 times 5 equals 25. So because 5 times 5 equals 25, I know the square root of 25 is 5. Well, sometimes we're not just looking at square roots. Many times we're also looking at what is other roots or cube. This is an example of a cubed root. And the reason it's a cubed root is because I'm not just looking at what number times itself equals that number. It's what number times itself 3 times. And so there's this little number outside my little square root bar, and that is the number. That value is talking about how many times am I multiplying by. So with square roots, there's technically a tiny little 2 out front, but we don't write that because we use square roots so often. When we get to cube roots or fourth roots or fifth roots, we write the little number outside the root to figure out, okay, how many times am I multiplying? So this is actually asking the question, what number times itself 3 times gives me 8? So what number times itself 3 times gives me 8? Well, 2 times 2 times 2 equals 8. So I know that the square root of 2 is 8. We can also use these on our calculators. On your calculator, you probably see the square root symbol. We probably used that in the past before plenty of times. For cube roots, fourth roots, fifth roots, you have a symbol that looks like this, and it probably has an A out front. And so when you type that in, it allows you to type in what is the number that you want to do out front. So you might have a third root, you might have a fourth root, you might have a fifth root. Like a fifth root would be saying what number times itself 5 times gives you that value. So that this is the button that you're looking for on the calculator when we're using these radicals. Roots and radicals are also the same word. If I say radical 5, it probably means the square root of 5, or root 5 means the same thing. So if I use the term radical or square root interchangeably, it's because they represent the same thing. Well, now let's try something else. How does this deal with exponents? So let's put 25 to the power of 1/2 in your calculator. So if you type in 25 to the power of 1/2 in your calculator, you're going to get 5. If we type 8 to the power of 1/3 in our calculator, we get 2. Now, that's kind of interesting because those are the exact same answers we got for square root of 5 or square root of 25 and the cube root of 8. 25 to the 1/2 is 5 and 8 to the 1/3 is 2. So it seems like rational exponents, rational means fractions, so rational exponents or fractional exponents are the same as radicals or roots. So there's some sort of relationship. And this is our exponent rule that we're going to talk about today. So when I have a radical, when I have a value raised to a rational exponent like a to the m over n, the numerator of that fraction is going to be an exponent inside my radical. The denominator of that fraction is the root of my radical. So for an example here, if I have 3, I'm taking the third root of x to the second, I know that this is the same as having my inside number is my numerator and my outside number is my denominator. So this is the same as having x to the 2/3, or vice versa. X to the 5/4 is the same as having my numerator is my inside number and my denominator is my outside number. So this is the same as having x to the 5th with the 4th root. The 4th root of x to the 5th, or the 3rd root of x squared is the same as x to the 2/3. So it works vice versa. Now, what we typically talk about simplifying exponents or simplifying terms, neither of these are more simplified than the other. They're equivalent. Most of the time, I prefer keeping my answer as a fractional exponent compared to as a square root. But neither of them, one isn't more simplified than the other. As long as all your x's and all your different variables are combined together using these, then that is perfectly okay. So let's look at some examples of these. So I have some rational exponents here. I have some fractions in my exponents. So I have 3x to the 1/7 y to the second times 6x to the 3/7 y to the 5th. So once again, when I want to solve these, I'm going to use those same strategies. I'm going to look by all my x's. So I have x to the 1/7. I have x to the 3/7. So these are all being multiplied together. So I just have to think, what is 1/7 plus 3/7? Well, 1/7 plus 3/7 is 4/7. So this is going to be x to the 4/7. Looking at my y's, I have y to the second and y to the 5th. So that's going to give me y to the 7th. And then my coefficients are going to stay normal. So 3 and 6 multiplied normally are going to be 18. So I have x to the 18, x to the 4/7, y to the 7. Now this could technically be the same as 18. And I could turn this rational exponent into a radical. So I could turn it into my denominator goes on the outside, my numerator goes on the inside. So this would be radical 7 x to the 4th, y to the 7th. These are the exact same thing, and they are both simplified. Personally, I like this version compared to the radical, but these are still equivalent terms. So this radical x to the 4th, radical 7, is the same as x to the 4/7. All right, so let's look at this one. Similar idea. I want to look at all my x's first, then my y's, then so on and so forth. So I have x to the 2/5, y to the 1/5. So 2/5 times 1/5 is 3/5. So we have x to the 3/5 as a rational. I have y to the 8 and y to the 2, so that's going to give me y to the 10th. And then lastly, I have 3 and 4 as coefficients. So coefficients multiply normally, which is just 12. So 12 x to the 3/5 y to the 10th. Now, once again, I could rewrite this as 12 5 radical x to the 3rd y to the 10th. This is okay. This is perfectly okay to write at. Personally, I like this version, but this is still okay to write at. It's still equivalent. And that's how we use our rational exponents. So the one last question. Which expression is equivalent to 144k squared r to the 14th all raised to the 1/2 for all positive values of k and r? So I know when I have as long as the inside is simplified, when I have a number on the outside, I can distribute that to each term, to each value inside my parentheses. So this is going to turn into 144 to the 1/2, k squared to the 1/2, and r to the 14th to the 1/2. Well, thinking back to yesterday, when I had an exponent to an exponent, they multiplied. So k to the second times, or to the 1/2, is really k to the 2 times 1/2. Well, 2 times 1/2 is 1, so this is k to the 1. And then r to the 14th to the 1/2 is 14 times 1/2, which is really just 7, so r to the 7th. Well, what is 144 to the 1/2? Well, if I think about it, 1/2 is the same as radical. It's the square root of 144 to the 1. Well, 144 to the 1 is just 144, so it's just the square root of 144. What's the square root of 144? Well, all of that is just 12. So this turns into 12. K to the 1 is just k, r to the 7th. So 12k r to the 7th, and that is our first term. And that is rational exponents. So that's where we're going to stop it for right now. We'll have plenty of time to practice over this today, along with our other exponents from previously, yesterday, or the day before that. And then we'll pick this all up next week and talk about this, or we'll review this a little bit more following week.